Hi, students. This is the fourth and final part of the Chapter 30 lecture on atomic physics. So this is about the longest chapter in the whole book. So it's, yeah, it is pretty much a monstrous sized chapter, but it is what it is. So, so what we've seen leading up to this point in the previous lecture, we've seen that there are different types of quantization. And again, this can be seen by solving the Schrodinger equation. All right, and so kind of reminders again when you solve the Schrodinger equation, all quantum mechanics rests on solving the Schrodinger equation. And I gave you the Schrodinger equation last time. Whose solution is a complex valued wave function. Complex meaning real and imaginary parts. So a complex valued wave function is psi. And again, this is the Greek letter psi, psi. Psi is it's pronounced kind of like you say the word sigh, psi, right? And so psi of the radial coordinate, the polar coordinate, the azimuthal coordinate, and really the time as well. All right, and again, this is the wave function. That's the answer to the partial differential equation, which is what the Schrodinger equation is. All right, now we understand that the total wave function psi, so the multivariable or multivariate wave function psi of r, theta, phi, and t can be expressed as a product of one-dimensional wave functions. And what I mean by that is that if I were to take the total wave function, multivariable wave function, psi of r, theta, phi, and t, I can actually perform what's called separation of variables. It's a process in differential equations that works for quantum mechanics. And that what it means I can take a multivariate partial differential equation and write it in terms of a differential equation for each of these spatial variables. And they can be separately solved. And so I can write a radial function, r of r. So the radial function is a capital R, is the name of the function, and it depends only on the radial coordinate r. And I have capital theta of theta. That's the polar function. Only depends on the polar angle. And I have capital phi of phi. And I can multiply that by capital T of T. I mean, what I'm doing is I'm separating these into separate one-dimensional functions. It works that way. It doesn't always work that way in differential equation, but it works that way for quantum mechanics usually. All right. And so what this means is that and remember here what this actually means. Quantum mechanics. So the quantum mechanics of an atom we're doing atomic physics. Is expressed in spherical polar coordinates. Due to the spherical symmetry of atoms. You choose a coordinate system because of the symmetry. You make the problem as easy as possible. All right, so, and what that basically means is it's a coordinate system. You think of it like a sphere. Think about there being a point on a sphere, and I want to identify what that point is. Well, here's a center. That point's going to have some sort of a radial r. It's going to have an angle coming from the North Pole, theta, and it's going to have some sort of an azimuthal angle, a distance around. So let's say a phi. And I can locate any point in the spherical symmetry by some r, theta, and phi, just like I can locate it in Cartesian with x, y, and z. So again, this is a alternative coordinate system that works very well for atoms. All right, and so what this means is I can divide out like this. That means that the single partial multivariate partial differential equation, or the Schrodinger equation, let's say this, the Schrodinger equation a single multivariate partial differential equation can be replaced spatially, I mean, in spatial coordinates. We're just going to worry about the spatial coordinates here. Turns out the time can be factored out by 3 ordinary one-dimensional differential equations. So one of them is in the radial. So the radial differential equation is called the Laguerre equation. and its solutions are R, capital R of R. One, the polar differential equation is called the Legendre differential equation. And it has solutions the theta of theta, if you will, the function capital theta of the polar angle little theta. And then the azimuthal differential equation, I don't really have a name for that. It's actually a pretty simple one. Has solutions cap phi of phi. All right, so we are able to tease out the Schrodinger equation into three separate equations that we can solve. And then we put these equations, we fit them into a space. All right, and then they become, the answers end up becoming standing wave solutions. All right, and so with standing waves, we know that there are integers that talk about the accepted resonances. Right, and so the integer, so the integers describing bound states, and all of this is done through the solutions of differential equations. None of this is accidental. It all has very tight solutions. The integers describing bound states of cap R of R are the principal quantum numbers. These are the same principal quantum numbers I've been talking about in previous videos. We call that N, principal quantum numbers, N. N can take on the values 1, 2, 3, so on and so forth. It can have positive integer values. And this is from solving the differential equation for R of R. Okay. Then we have solving the polar equation. The integers describing the bound states of cap theta of theta, the polar solutions. R, this is the orbital, the angular momentum quantum number. And we usually call it, I usually have it as a small L, a script L, so it doesn't look like a 1. That's the way I write it. L can take on the values. Well, L can have the values, the following values. L can equal 0, 1, 2, dot, dot, dot to n minus 1. It can have any value, any non-zero value up to one notch below whatever n is. It cannot equal n or exceed n. So L can take on 0, 1, dot, 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 all the way to n minus 1. So if n equals 3, then your principal your angular momentum quantum number can only be 0, 1, or 2. Right? Again, this is the angular momentum quantum number. And I'm going to mention in a moment, it is the quantum number that provides the quantization of the magnitude of the angular momentum. We'll talk about that in a moment. Okay, I'm just talking about the mathematics right now. And then we have one more. We have the phi. The phi, and that's going to be, when you solve that, that is also going to have a number that's going to cause so basically in the same token, again, I'm just doing mathematics here. The integers, and these are all integers. The integers describing bound states of cap phi of phi. This is the azimuthal function. Are officially the angular momentum projection quantum number. The angular momentum projection quantum number. M sub L, as it's called. M, so this would be pronounced M sub L. That's how you pronounce it. All right. Now, what are the possible values of M sub L? Again, it's integers. M sub L can take on the following numbers. So M sub L can go all the way from negative L plus 1, dot, 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 negative 1, 0, positive 1, dot, 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 to L minus 1, all the way to L. It ranges from negative L to L. All right. There's a dependency in all of these quantum numbers. Yes, they are separately. So again, this is the, let me get another pen here. This is the angular momentum projection quantum number. I'm going to talk about physically what all of these mean. I mean, I've already just kind of very much directly progresses from my previous video, but all of these again have physical meaning. All right. So again, this is the angular momentum projection quantum number. All right. So if you solve for cap R of R, you get the integers that correspond to the bound states are going to be given by the principal quantum number n, 1, 2, 3, dot, dot, dot. Integers describing the bound states of the polar angle, cap theta of theta, are the angular momentum quantum number L. Again, there's no accident of this called that. I'll explain that in a moment. It has the values of L is 0, 1, 2, dot, 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 to n minus 1. Then the integers that describe the bound states of the azimuthal function, cap phi of phi, are the angular momentum projection quantum numbers, M sub L. M sub L can take on the values of negative L plus 1, dot, 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 negative 1, 0, positive 1, dot, 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 L minus 1 to L. All right, now, what do these mean physically? Well, first of all, the principal quantum number, we saw that when we talked about the quantization of energies. All right. So let's kind of talk about what these quantum numbers mean physically. And again, we talked about the quantization of energies, quantizations of orbits, but effectively the energy states of a balanced system are quantized. Okay, that's number one, because a particle wavelength, we talked about this last time, because a particle wavelength can fit into the bounds of a system in only certain ways. Okay, again, we saw that we're trying to fit a particle, let's say, on an orbit. Okay, and so we know, for instance, for the hydrogen atom, we learned that from that the hydrogen atom has bound state energies that go as 1 over n squared. E proportional 1 over n squared. We learned that. Again, where n equals 1, 2, 3, ... All right. So the n is the principal quantum number. The same principal quantum number. Okay, so again, this is a number that defines a main orbital of your system. So the allowed values, again, n can take on the values 1, 2, 3, ... n equals 1 is the ground state. And we've been using this language for a while now. And then, this is not just a counting scheme either. All right, this is not, not just numbering scheme. Literally, the energies, the radii, all depend on this value. This is a characteristic value of a quantum system. You understand that? It is not just a labeling scheme. Okay, these are numbers that describe a quantum system. They are characteristic numbers that describe a quantum system. Okay, so again, this is not just a numbering scheme. Don't just think this is a labeling scheme. The principal quantum number n is a characteristic parameter of a quantum system. All right, energies. In orbital radii. Spectral lines. Are all functions of n. Okay, so n is a characteristic of your system. It is not just a Levy scheme. It's the beauty here of the universe is that there are these beautiful integers that describe atomic systems. Okay, what about the orbital angular momentum quantum number? Okay, that's a principal quantum number. All right, the next one we talked about was the solutions, the integers that describe the polar angle cap theta of theta. Well, the magnitude of the angular momentum is quantized. Okay, we talked about that in the last video. The magnitude of the orbital angular momentum is quantized. As first recognized by Niels Bohr. Okay, so again, the magnitude of the orbital angular momentum is quantized. Extremely important piece of information right there. Now, it turns out that when you do the mathematics to solve the angular momentum or the polar angle solution, again, a lot of this, the mathematics is beyond the scope of the class. I'm really just going to give you results. Turns out that the magnitude of the angular momentum, which we call L, is given by the square root of L times L plus 1. A square root of just that times h over 2 pi. Okay, these are, so angular momentum as described by the orbital angular momentum, or by the angular momentum quantum number L, little l, has quantized magnitudes or magnitudes, if you will, and what value of L you feed it, cap L. So if my solution, I know the electron is in an L equals 1 state, for instance, I can say 1 times the quantity 1 plus 1, or 1 times 2, the square root of that times the Planck's constant divided by 2 pi, and I know the magnitude of the orbital angular momentum of the electron. The orbital angular momentum is quantized. It can only take on values given by this equation. Again, the magnitude of the orbital angular momentum is quantized. Only certain allowed values That's it. Not all values. Only the values given by the orbital angular momentum or the orbital quantum number L. Whatever the solutions to the differential equation, or whatever, given whatever value n is, whatever possible integer values L can take on, the orbital angular momentum of an electron can only take on those values. That is it. It's the orbital, the magnitude of the orbital angular momentum is quantized. That's the actual kilograms meters squared per second answer. Now these L's are integers. You know the L, you put it in here, you multiply by Planck's constant divided by 2 pi, and you get the orbital angular momentum. You get the actual measured orbital angular momentum this way. All right, so the for instance, kind of give an example here. Let's just say that, you know, n equals 3, for instance. All right, so if n equals 3, just say n equals 3. If that's the case, then what are the possible values of L? What are the only values L can take on? Well, it can only take on 0, 1, or 2. Remember, it can only go from 0, 1, 2, all the way to n minus 1. N minus 1 would be 2. I cannot ever have an orbital quantum number equaling the principal quantum number. That is not legal. All right. So the values I can possibly put in here, let's just say say L equals 2 for a particular electron. It would be said that the electron is in the L equals 2, what is called orbital, or we're going to call it a subshell. I'll talk about shells and subshells in a minute. What would its angular momentum be? Well, I would figure out like this. I say, okay, well, L, if I know that the orbital quantum number is little l, I know what it is. Like say 2. Well, I just put it into the formula. Remember, L is, so big L is the square root of L times L plus 1 square root times h over 2 pi. Okay, L will be 2 times 2 plus 1 square root of that times h over 2 pi, which will be, let's see, 2 times 3 is 6, so it'll be the square root of 6 over 2 pi. And what's h? 6.626 times 10 to the negative 34 joule seconds. And I find out that when I do that calculation, that L for that electron will be 2.583 times 10 to the negative 34 kilograms meters squared per second. All right, so that is an honest to goodness value for the angular momentum of the electron, given that I know it has the solution given by the particular quantum number L equals 2. And typically, it's a lot easier to refer to a L equals 2 electron than an electron that has 2.583 to the negative 34 kilograms meters per second. It's a lot easier. It's much easier to refer to. So it is a lot easier to refer to an electron in an L equals 2 with L equals 2 as an electron with such a value. We'll say an L equals 2 electron. Now, we actually have a notation that we use. Okay, that again, many of you have seen this notation in your chemistry class, but in general, we have a spectroscopic notation that's given by NL. So essentially, you take an electron. So if an electron has a certain value, a certain, or can be described, let's say, by a certain principal quantum number n, and by a certain orbital angular momentum quantum number L, we describe it by a digraph NL, where n is an integer, n is the numerical principal quantum number, and L is a letter designation. You can think of L in this way. I can say, well, if I know my L, what is the letter that describes it? All right. So let's say, for instance, I can go 0, 1, 2, 3, 4, 5, so on and so forth. What letters would describe that? Well, the designation is kind of an old spectroscopic designation, but the L equals 0 is given as the letter S. L equals 1 is given by the letter P. L equals 2 is given by D. And L equals 3 is given by F. And then it goes in order, G, H, I, and so on and so forth. So in my previous example, if n equals 3 and L equals 2, this would be considered a 3, let's see, 0, 1, 2. This would be a 3D electron. It's given as NL, 3D. N equals what? 3. L equals what? Well, L equals really 2. You see, L equals 2. Oh, that corresponds to D. It'd be considered a 3D electron. All right. So again, that's usually the better and easier way of describing an electron. You're not going to want to describe an electron by this. I mean, in some cases, yes, you will need to talk about the actual value of the orbital angular momentum, but the reality is, it's a lot easier to say I have a 3D electron, and that's a lot easier notation. And we'll talk more about that in our next section. So Now the to kind of mention one more time is, again, a lot of our derivations of all of this were done with the assumption of, we kind of utilize the Bohr model for our purposes here to make things understandable. Understand, in general, I'm just repeating this here, but the picture of circular orbits is not valid. Just reminding you of this. Okay, picture circular orbits not valid because there would be angular momentum for any circular orbit. Let me give a little special example here. This is where Niels Bohr was wrong. A circular orbit would mean, yeah, there must be angular momentum for any kind of particle going around the circle. Well, let's return briefly to the Bohr model of the hydrogen atom. But let's look at it from the perspective of true quantum mechanics. Schrodinger quantum mechanics. All right. So ground state means what? N equals 1. Okay, well, let's see here. If n equals 1, what are the possible values of L? Remember what L? L can have the values of what? Negative, it can have the values of 0, 1, 2, ... all the way to n minus 1. Oh, okay. N minus 1, what's that? 1 minus 1 is 0. That means the only value of L is 0. So L can only be 0 for the ground state of the hydrogen atom. So an electron in this state has no angular momentum. Or has 0 angular momentum, which contradicts Bohr. So Bohr is wrong in this case. Again, where Bohr was right is that angular momentum is a quantized quantity. But if a ground state of hydrogen atom, it is not. There is no NH over 2 pi for angular momentum. It is not true. Angular momentum for the ground state of quantum of the hydrogen atom would be 0. If n equals 1, L can only be 0. which means a capital L would be 0. All right, and so a more useful model, again, is the concept of the cloud of probability. You know, the solution to the Schrodinger equation gives you the wave function. You take a complex square of the wave function, you get the probability density or probability distribution function. All right, so again, the better model is to see the electrons in the atom as described by a distribution or a probability distribution where it is in a cloud of probability. I talked about this in the past. Described by the complex square of the wave function. Complex meaning real and imaginary. So complex square would be the complex conjugate. And that's if I take every single imaginary value and take it and switch the sign on it, SIGN, of R theta phi, and multiply that by the wave function itself. I'm gonna not worry about the time dependence. Where, well, where psi of R, theta, phi, and T is a solution to the Schrodinger equation for the system. I mean, I talked about this in previous videos. All right, so again, you have to describe quantum mechanics as fundamentally the physics of the atom, the physics of the submicroscopic. Is fundamentally based upon probability theory. The universe, unlike, to Einstein's chagrin, the universe, God does throw dice with the universe. I mean, the basis of the universe is probability. Okay, now the electron actually spends time in the nucleus itself, believe it or not. It just doesn't spend a lot of time there, because then you would have you would know where the electron was to a very small uncertainty, and that would be, and so the Heisenberg uncertainty principle ensures that the electron does not spend very much time in the nucleus. So again, the electron spends time in the probability cloud, including inside the nucleus. So again, the location of the electron of an electron in an atom is described, as I just said, by a cloud of probability. And the electron, the electrons actually spend a little time in the nucleus itself, but in a limited sense, due to the Heisenberg uncertainty principle. So this is the true quantum mechanics. Okay, the electron, the electron has a definite location. Nature just doesn't want to let us know what it is. Okay, now we've talked about N, we've talked about L. What's next? Well, we have M sub L. M sub L is the next. That is the angular momentum projection quantum number. And what does it do? Well, that's what governs the Zeeman effect. As we saw, there are the quantization of the direction of angular momentum is separately quantized from the magnitude. The magnitude of the orbital angular momentum is quantized, and separately the direction of the angular momentum is quantized. Again, we're really revisiting the quantization conditions mathematically. All right, so as recognized in the Zeeman effect. Again, when you apply an external magnet, the spectral lines will split into 2 or even 3, will split into 3, 5, so on and so forth. That depends on what's called the Zeeman effect. So again, as recognized. In the Zeeman effect. The direction of angular momentum is quantized. Separately quantized. Okay, so again, what we have to talk about is what do we mean by direction? And so the direction of the orbital angular momentum is with respect to the z-axis. And so what makes one direction more important than another? Well, a direction is only important if something changes in that direction. and I've talked about this before. So what do we choose as a z-axis? What's that special axis? You know, from relativity theory, an axis or a direction is only significant if something physically changes in that direction. So with an applied external magnetic field, the direction of the magnetic field forms the z-axis. That's what makes one direction more significant than any other. That's what makes a special direction. Is the direction of the z-axis, or sorry, the direction of the magnetic field, because that's the only place where something physically is changing. All right, and so what you think about here then is if your orbital angular momentum is some value of L and at some sort of an angle theta, and let's say, for instance, for argument's sake, that we consider the magnetic field as being straight up. This is B external. Well, that's also going to form my z hat axis, my z-axis. So if I have some sort of an angular momentum, it has some sort of an angle, okay? I would refer to this component as L sub z. And so I would know that the cosine of theta is L sub z over L. Again, it is, and so I can refer to this as L sub z as a magnitude of L times the cosine of the angle. Okay, why a cosine? Because it's adjacent over hypotenuse. And I can think, of course, this is a component, so that would be a right angle. All right. So again, we are saying here that the magnitude of the angular momentum is quantized, and separately, the z component of the angular momentum is also quantized. They're separately quantized. All right, which means that if L sub z is quantized, given a value of L, that means that there can only be certain angles that are accepted. I mean, I wrote that kind of diagram on the board earlier, but what is the rule for this? Well, it turns out, if you do the mathematics, it turns out that angular momentum, the z component, is specifically quantized according to the following relation. M sub L times h over 2 pi. And then, as I said earlier, M sub L is the angular momentum projection quantum number. angular momentum, projection quantum number. It can only take on the certain values again. M sub L can have the value negative L plus 1, dot, negative 1, 0, 1, dot, L minus 1 to L. It can range in integers from negative L to L, where L is the orbital orbital angular momentum quantum number we talked about for and from the polar solution. Again, these relationships they're all related. Now, this tells you that the Z component of the orbital angular momentum of an atomic electron is quantized the previous relation told you that the magnitude of the orbital angular momentum is quantized. So here, the Z component is quantized. That's the direction of the angular momentum is quantized. The magnitude is separately quantized. So the L, little l, quantizes the magnitude of the orbital angular momentum, and M sub L quantizes the direction, or specifically the Z component of the angular momentum. So the angular momentum of the electron can only have certain quantized magnitudes and certain quantized directions. All right, and so let's just say, for instance, that I go on my previous example, and I remember L equals 2. So, okay, fine. Let's say n equals 3, going back to my example, and little l equals 2. What are the possible values of M sub L? Well, again, M sub L can go from negative L to L. So I can have negative 2, negative 1, 0, 1, or 2. That's it. Those are the only possible values. So in this particular case, if L equals 2, and if I was pH or Zeeman, and I was putting a magnet, an external magnetic field, I would find out that my spectral lines are split into how many? 1, 2, 3, 4, 5. My spectral lines are split into 5. I would see 5 spectral lines, all of which would have different energies. So in the Zeeman effect, what Zeeman was seeing was the different values or different states of the possible states of the electron. All right, so let's calculate some. Do an example. I'm gonna do open set example 30.3. Let's kind of chew on this idea a little bit more. I'm gonna do OpenStax example 30.3. All right, OpenStax example 30.3. And that example is what are the allowed directions? All right. So I want to take a look at, I'm going to find out for an L equals 1. So let's consider L to equal 1. Okay, we're going to say that we have an electron that is in an L equals 1 system. What are its possible? So let's consider an L equals 1 electron. what are its possible values, or I guess what are its possible angles, I guess. What are the possible angles of L, the angular momentum from the z-axis? So you look at the picture, you can think of like, well, here's my z-axis. Now I can have let's just say, well, let's first of all say, okay, we'll find out. We know that the directions are determined by m sub L, right? So if L equals 1, that means that m sub L again can go from negative L to L by integers. So it would be negative 1, 0, or 1. That means I expect to have 3 splittings. Let's kind of write it like this: 1, 2, and 3. Now, again, if the electron is orbiting at any of these, it's going to be orbiting, let's say, in a circle. Apologize for my bad drawing here. This is my z-axis. Now, like in this particular case, this would be my value of L sub z. This would be my value of L, magnitude of L. All right. So again, we're talking about 3 different orbitals for the electron. And so this would be m sub L equals positive 1. M sub L equals 0. M sub L equals negative 1. Let's show you how we get this. Each one of these are going to have an angle. So I'm just looking at like let's say the top one. All right. So it's kind of, let's concentrate on the top one. So again, what we're seeing is L is 1. So again, we kind of make things more compact. M sub L can take on the values of negative 1, 0, or 1. Let's consider the top value. Again, these are supposed to be orbitals. I apologize. Bad pictures here. Let's consider m sub L. Let's consider L m sub L to be equal to this pair being 1, 1, 1, 1 positive 1. All right. So 1, 1. We're going to consider that particular combination. L equals 1, m sub L equals 1. All right. So what does that come down to? Well, in general, what did I say before? Well, I said the cosine of theta was going to be L sub z over L. What is L sub z? Well, its form is what? It's m sub L times h over 2 pi. Those are the allowed values of L sub z. What about L? L has allowed values square root of L times L plus 1 times, again, h over 2 pi. So essentially, for me to determine the angle, this is from trigonometry, see adjacent divided by the hypotenuse. Well, again, L sub z is quantized. It can only take on the values m sub L times h over 2 pi. So again, that's the z component, i.e. the angle. L, the magnitude, capital L, the magnitude of the angular momentum can only take on the values of square root of L times L plus 1 times h over 2 pi. Well, what's nice is this h over 2 pi's cancel out. And so what I get in solving for the cosine, what I want to get here is that theta is the inverse cosine. And what's left? The only thing left on top in the numerator is m sub L. And on the bottom is the square root of L times L plus 1. There it is. Okay, well, that's my general formula. What am I talking about now? Well, I'm talking about what? L equals 1, m sub L equals 1. So in this particular case, I'm looking at theta. I'm trying to squeeze it in here. Theta is the inverse cosine. Obviously, m sub L is 1, and L is going to be square root of 1 times 1 plus 1. Theta is the inverse cosine of 1 over the square root of 2. You do that, you get that theta is 45 degrees. So one of your allowed values, the allowed angle for the orbital angular momentum and the z component is 45 degrees. Not 44, not 40, 45. Again, that orbital angular momentum it's going to have a corresponding orbital right there, like in the shape of a funnel. And it can only have that particular angle. So again, this is in space, here is your z component for magnetic field. All right. The orbital angular momentum vector will not align with the z component. Okay, it will not. It can get to 45 degrees. What about the other allowed angles? So theta equals 45 degrees is one of them. This will be the top angle, 45 degrees. What about the other two? Well, again, I'm going to do a little erasure here. But now what's the other one? Let's see. What's the m sub L could be 1, 0, or -1. Let's make it 0. What happens now? So L m sub L is now going to be 1, 0. Means everywhere you see m sub L, you put 0, and L is going to continue to be 1. So again, over here, this becomes 0, and this all becomes 0. 0 divided by anything is 0. Inverse cosine of 0, 90 degrees. That is another allowed direction of the orbital angular momentum. 90 degrees. That would be this one here. B, the z-axis, and the orbital angular momentum L form a 90-degree angle here. Okay, this one here, theta is 90 degrees. That's another accepted angle. What about the last one? Well, again, the only other value that m sub L can take on is -1. We'll put -1 here now. Consider L m sub L, 1, -1. Everywhere you see m sub L, you put -1. L still remains as 1. This becomes -1. And of course, this is going to become what? -1 over the square root of 2. And that's going to give you 135 degrees from the positive z-axis, which is 45 degrees for the negative z-axis. So this final angle will be theta of 135 degrees. Now, imagine for a moment what this means, that if you have a solution, a p electron, for instance, again, SPDF, L equals 1 means p. Okay, if you have a p electron, it can only have angular momenta. I mean, again, its magnitude angular momenta is going to be determined based upon the this formula L squared L times 20 L plus 1 times h over 2 pi, and its directions, the z components, are only going to be determined by this m sub L times h over 2 pi, which means there will only ever be 3 configurations of angular momentum that will ever be accepted. They are quantized. Only these directions of angular momentum are allowed. No other direction of angular momentum are allowed. Your orbitals are going to be governed by at 45 degrees, 90 degrees, 135 degrees. That's it. 135 being, again, everything from the positive z hat axis. Those are only the only 3 allowed directions of the angular momentum vector for the electron. Those 3 directions and only those 3 directions. So the magnitudes of the angular momentum are quantized. If L equals 1, it's only going to be, the magnitude is only going to be given by square root of 1 times 20, 1 plus 1 times h over 2 pi. That's it. That is the only, and I calculated, that was that number I calculated earlier. For the directions, the z component is only going to have 3 possible values for L equals 1. And that means that there's 3 angles, 3 configuration angles in space, period. Quantum mechanics is vastly different than our everyday experience. Angular momentum and its direction can have any value you want. If you talk about the Earth going around the sun, it can have, or a moon going around the Earth, it can have really, hypothetically, any angular momentum, magnitude, or direction. There's nothing that's that would prevent that. But in quantum mechanics, the physics of the submicroscopic, your magnitude of the angular momentum and its direction are separately quantized. Okay? Okay, so we talked about N, L, and M sub L. But if you go back to the last video, we also talked about the fact that the every spectral line is really a doublet. If you look closely enough, it's really 2 very finely associated spectral lines. Okay? We learned that this is caused by what is called quantum mechanical spin. You imagine, kind of loosely, look at the Earth, for instance. The Earth goes around the sun in one type of motion. That's the orbit around the sun, but it also, as it's going around, it's spinning on its axis, right? So there's 2 types of angular momentum going on with the orbiting particle. So we can think of this analogously as the spin, even though it's, when you look at the answers to it, it's going to be very weird, much different than you could ever imagine. So again, as we recall, there are 2 more quantum numbers of immediate concern. Besides N, L, and M sub L. We have these 3. So it's now well established electron has, and other fundamental particles have intrinsic spin. So it is now well established that electrons and other fundamental particles, not just electrons, other particles too, have intrinsic spin. roughly analogous to a planet spinning on its axis, as I said. Okay. So the spin is a fundamental characteristic of particles and only has one magnitude. All right. So what's strange about it is the spin is a characteristic of a particle, of a type of particle. And each type, each one has one value of spin. That's it. All right, and so for the electron, so essentially we have some new quantum numbers. So the magnitude and the direction of the spin angular momentum are also quantized. All right, and so there is, so for the electron, or an electron, any electron, remember they're all identical. There's a concept of indistinguishability. Any electron has a spin quantum number s, little s, of 1/2. That is it. Okay, so the spin of an electron has a value of 1/2. Now, there are other, it turns out that the fundamental spin, or the spin quantum number, for protons and neutrons is also little s equal to 1/2. But there's other kind of particles, for instance, photons. Have s equals 1. Pions, we've talked about pions before, fundamental particles, have s equals 0. So there's a quantum number, little s. And any particle, any type of particle, every single electron you can ever point at has a little s value of 1/2. All of them, every single one in the universe. Every neutron and proton has s equals 1/2. Everyone in the universe. Every photon, particle of light, has s equals 1. Every single pion, which is a fundamental particle you see in high-speed collisions, like in accelerators, has s equals 0. Every single one has a special value of the spin quantum number. Now, we can go for the spin quantum number, and we're going to talk about electrons here. We can go for the spin quantum number and get the spin angular momentum. All right. So the spin angular momentum, so again, the magnitude of the spin angular momentum we'll call that capital S, is quantized and given by capital S is, again, we're talking about the magnitude. Capital S, I'll put the hat off the vector here. Capital S is given by the square root of little s times little s plus 1 times h over 2 pi. It looks very similar to the angular momentum. Again, unlike the angular momentum, which should take on various values of little l, little s has 1/2 or electrons. That's it. Okay? So that's one thing. The magnitude of the spin angular momentum, big S, is quantized. Okay? So again, the magnitude of the spin angular momentum, big S, is quantized. Separately, the direction is quantized. The direction of the spin angular momentum is quantized. So the direction of spin is quantized. Separately quantized. And if you talk about, again, the letting with the z direction being the direction of the external magnetic field. The directions of the z component of spin. Only has the values S sub z, cap S sub z, z component is m sub s h over 2 pi. Okay, m sub s is the spin projection quantum number. It only takes on 2 possible values. M sub s can equal positive 1/2. We call that spin up. Or negative 1/2. We call that spin down. Spin up or spin down. That's it. Those are the quantum numbers of quantum mechanics. Those are again, the S is always 1/2 for electrons. And this is the let's see, S is the spin quantum number, which I wrote someplace. Yeah, I wrote it previously. This is a spin quantum number, and the spin projection quantum number are the directions of the spin angular momentum. And again, they're very similar in the form of the equations for the orbital angular momentum, but different. Spin is much more limited in that little s can only have the value of 1/2. In fact, it only has a certain given value for any particular particle. So S is only 1/2 for electrons. S is only 1/2 for protons and neutrons. S is only 1 for photons. And S is only 0 for pions, for instance. And then the spin precision quantum number for electrons is spin up or spin down. M-S is plus 1/2 or negative 1/2. That's it. Those are the only values that are possible. All right. And so now as I said, the other subatomic particles have different values of the spin S. And in fact, it turns out that they obey different statistics depending upon what values they have. All right, and so I'll talk more about that in a little bit. So let's kind of sum up what we now know. Make a little table here. And it's a lot of information. So I'm really recreating table 30.1 from OpenStax, but again, let's talk about what we have here. So all together we have, let's talk about the name of our quantum number. We'll talk about its symbol. And we'll talk about the allowed values. All right, so the first one, of course, is the principal quantum number. And its symbol, I'll write the symbol closer over to here, is the letter N, little n. It takes on positive integers. It's allowed to have the values of n equals 1, 2, 3, so on and so forth. Okay, it can never be 0, and it can never be negative. It can only have integers that are positive. Okay, we talked about that. We have the angular momentum quantum number. And I'm just looking at the quantum numbers. Okay, angular momentum. Angular momentum has a symbol, little l. I always use a little script L. And it can have non-negative values up to n-1. So it can have the values, so little l can have the values of 0, 1, 2, ... Integers up to n-1. It is limited by n. In fact, it can never equal n. It can only be 1 less than n. Those are the allowed values of the angular momentum quantum number L. Then we have the angular momentum projection. We call that M sub L. M sub L, it also has its integer. It has integers, but it can be negative. It can be negative L plus 1, ... -1, 0, 1, dot, 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 L minus 1 to L. It's limited by the orbital or by the angular momentum quantum number. Then you have the spin. The spin quantum number is given by a little s, and it can only be the value of 1/2 for electrons. And for any given fundamental particle, it has one value. For electrons, protons, neutrons is 1/2. All right, and then you have spin projection. Spin projection in this case is given by m sub s, and it can only have the values of positive 1/2 or negative 1/2. That is it. Again, those are the allowed values of that these quantum numbers can have for electrons bound to an atom. Let's work a few problems out. I'm going to work out OpenStax 30.35. Okay, 30.35 says, if an atom has an electron, in its n equals 5 state, with m sub L equal to 3, what are the possible values of L? Okay, so again, you're limited by what you can choose. In fact, the limitation imposed by the relative or by the relative constraints of one quantum number, or of the quantum numbers are called limitations, are called selection rules. They're called the selection rules. You know, the selection rules govern allowed and unallowed sets of quantum numbers. N, L, M sub L, S, M sub S. Now we have to employ the relations of N, L, and M sub L with this problem. Okay, we're employing, this is a problem that deals with what we call selection rules. All right, so let's go back to what we recall here. So, all right, well, N equals 5. That means that L can have the values 0, 1, 2, 3, or 4. I can't get less than 0. I have to be an integer, and I cannot exceed. I mean, I'm limited by n minus 1. So n minus 1 or 4 is the largest value that L can take on for this particular electron. But I'm being told that M sub L is 3. So we are told that M sub L equals 3. Well, M sub L is limited by what? Negative L plus 1, dot, 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 negative 1, 0, positive 1, dot, 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 L minus 1 to L. That means that whatever the value of M sub L is, it can't be any more. I mean, essentially, L cannot be less than M sub L. Let's put it that way. M sub L can only be as small as negative L or as big as L. So, for instance, if I said, well, can L be 2? Can little L be 2? Well, if that was the case, what if L equal 2? Then what? Then M sub L would only be able to equal negative 2, negative 1, 0, 1, or 2. But M sub L equals 3. That means that L cannot be 2, L cannot be 1, L cannot be 0. There's no way that L can be 2 and have M sub L to be 3. L has to at least be 3. If L equals 3, then M sub L can take on the values of negative 3, negative 2, negative 1, 0, 1, 2, and 3. Great. That means that M sub L can be 3 because L equals 3. But in the particular situation, this little L, it's limited what? It's limited by 4. So L can actually equal 4 as well. Little L equals 4. That means that M sub L can take on the values of negative 4, negative 3, negative 2, negative 1, 0, 1, 2, 3, 4. And that's okay. Because I know that M sub L is 3, but it could be 4. Nothing that stops it. The only thing is it can't be less than 3. M sub L can only be negative L to L. There's no way that I can get an M sub L equal to 3 based upon an L equal of 2. If L equals 2, that means M sub L is maxed out between it's small as it can be is negative 2 and the largest it can be is 2. If M sub L equals 3, the smallest it can be is negative 3, the largest it can be is 3, and that's okay because M sub L equals 3 is part of that range. And I can make it 4 as well. The smallest M sub L can be is negative 4, and the largest is positive 4. Well, L equals 3 is right there. It's in that range. Perfectly okay. But I can't make L any bigger than 4. It can't, because it has to be 1 less than 5. So the answer is, after this rationale, is that L can take on the values of 3 or 4. Those are the possible values of L to make this work. Okay, this is the kind of logic that one has to do in problems like this. L, if you know that M sub L is 3, you know that L cannot be smaller than 3. Okay, but L can be 4, and even if it's 4, perfectly okay. There's M sub L. It's part of that range. No big deal. But L cannot be bigger than 4. It cannot equal 5, for instance, because it's limited by the selection rules. L can only be at most n minus 1. So that the angular momentum quantum number L can be 3 or 4 for this electron. Okay, look at Opus X 30.36. .36 says an atom has an electron with m sub L equal to 2. All right. Atom has an electron with m sub L equal to 2. Okay, that's just a given. What is the smallest value of n for this electron? All right. All right, so now we're being given that there is an electron in this atom. I know for a fact that m sub L is 2. All right. Now, what does that tell me? You know, based on the last logic that we just had regarding L, well, that means that L, we know that m sub L, again, is constrained to be between negative, I'm sorry, to be constrained to be negative L plus 1, dot, 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 negative 1, 0, positive 1, dot, 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 to L minus 1 to L. So if m sub L is 2, that means that, minimally speaking, L better be 2. L can't be 1. If L was 1, I mean, if L was 1, the m sub L could only take on the values of negative 1, 0, or positive 1. 2 is not in that range. So L cannot be 1, L cannot be 0. If L equals 2, then m sub L can take on the values of what? Negative 2, negative 1, 0, positive 1, positive 2. Great. Okay, now, we're looking for the smallest value of n. So L equals 2 is the smallest value of L. All right, so L equals 2 is the smallest value of L. Because, of course, the smallest value of n will have to correspond to the smallest value of L. I'm trying to minimize stuff. Smallest value of L. Now, how does L relate to n? Well, remember, L can take on the values of 0, 1, 2, dot, 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 all the way to n minus 1. That means that, well, okay, if the smallest value of L is 2, we're going to go with 2, that means that n has to be at least 1 bigger. So that means that the smallest value of n is 3. I mean, you could have n equal to 4 or 5 or any other value. I mean, any other n. I mean, the minimum value that n can be is 3. It could be 17. I mean, it doesn't really matter. The reality is, the smallest it can be in this selection scheme is 3. And that's the answer to the question. Again, it's all balancing out the selection rules. Again, so again, let's recall, I was given m sub L equals 2. I know if m sub L equals 2, then L has got to go from negative L. M sub L can only range from negative L plus 1, dot, 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 negative 1, 0, positive 1, dot, 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 L minus 1 to L. So again, L cannot be 1 because 2 would not be in that range. So the minimum value that L could be is 2. L could be 3 or 4 or whatever. But the reality is it must be minimally 2. Again, we're looking for smallest. So if I want the smallest n, then the smallest n will occur with the smallest L. Now, what's the relationship between L and n? Well, it's going to be 0, 1, 2, dot, 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 n minus 1. that means that L can only be at most 1 less than N. All right, and so in this particular value, I'm sorry, why did I write that down? N is 3. N has a value of 3. The minimum value of N is 3. Okay, so again, the minimum, so again, the minimum value of L is 2, the minimum value of N is 3. I apologize, talking and got confused myself. Right, so again, the minimum value of N is 3, because why? Because N has to be, L has to be no more than 1 less than N, according to the selection rule. All right, so N is 3, because L has to be minimally 2 in order for M sub L to be 2. And given that L equals 0, 1, 2, N minus 1, L can be at most 1 less than N. That means that if we're going with the minimum value of L, the minimum value of N has got to be 3. Okay? Sorry about that little mistake earlier. All right, let's look at another. Again, this is the nature of these selection rule problems. Let's look at another problem here for OpenSX 30.39. All right, so what does that say? A, calculate the magnitude of the angular momentum for an L equals 1 electron. So calculate the magnitude of the angular momentum for an L equals 1 electron. Okay, that's part 1. And then that's A, then B. B says, compare your answer to the value Bohr proposed for the N equals 1 state. All right. Okie dokie. So for part A, again, we're looking at an L equals 1. That's what we're talking about. L equals 1 for the electron. What is the angular momentum? Well, again, the angular momentum, the actual quantity that's in kilograms meters squared per second, is going to be given by the square root of L, 20L plus 1 times H over 2 pi. All right? So that's going to be the square root of 1 times 21 plus 1 times 6.626 times 10 to the negative 34 joules seconds divided by 2 pi. Again, that's Planck's constant. So L will be, this will end up being the square root of 2, again, times 6.626 times 10 to the negative 34 joule seconds over 2 pi. And this works out to be 1.49. Times 10 to the negative 34 kilograms meters squared per second. That is an honest to goodness calculated value that you get from these quantum numbers. That is an angular momentum that you would measure for an electron. That is the angular momentum like we would calculate any other angular momentum. You're getting this from this particular formula. If you know the quantum number L, little l, the orbital angular momentum quantum number. You put in the square root formula, multiply by the Planck's constant divided by 2 pi, you get a value that is in kilograms per meter squared per second. Now, what did Niels Bohr propose? Well, in the Bohr model, Bohr proposed that the angular momentum looked like this. The angular momentum was m sub e v r sub n. Again, we're looking for n equals 1, is nh over 2 pi. Where n equals 1, 2, 3, dot, dot, dot. Again, that's Bohr. Niels Bohr's theory is not correct. It is a beginner training wheels theory, if you will, for quantum mechanics. It's not, I mean, it had a lot of, great. Bohr won the Nobel Prize. Bohr was able to successfully describe the orbits of hydrogen orbits, electrons and hydrogen. Again, it's only good for an atom that only has one electron going around it, remember. And it successfully described the bound state energies, the bounds and the orbits of the electrons. And it also was able to predict the spectral lines. All of this was, predicted by Bohr. Bohr laid down the seeds of quantum theory, but remember, Bohr's formulas are not in general correct. Okay, in fact, they would be completely incorrect for anything that has 2 or more electrons, any atom with 2 or more electrons. All right, so we're looking at n equals 1 here again for Bohr. So Bohr would propose that your L would be 1 times h over 2 pi, or 6.626 times 10 to the negative 34 joules seconds divided by 2 pi. So Bohr would propose that the angular momentum of this of an n equals 1 electron, if you will, in his model, would be 1.05 times 10 to the negative 34 kilograms meters squared per second. I mean, that's what Bohr would propose. And this is not correct. All right, so another problem. Opus Ax 30.40. A. What is the magnitude of the angular momentum for an L equals 1 electron? Okay. And B says calculate the magnitude of the electron spin angular momentum. All right, and then C says, what is the ratio of these angular momenta? All right. So here we go. A, what is the magnitude of the angular momentum for the L equals 1 electron? B, calculate the magnitude of the electron's spin angular momentum. C, what is the ratio of these angular momenta? All right, so we're going to use these quantum mechanical formulas directly. So again, let's remember this. I need real estate. All right, so we want the angular momentum. What we know is that the orbital angular momentum quantum number is L equals 1. All right, we know that. Now, the formula for this, again, to get from angular momentum quantum number to an actual angular momentum is cap L, and again, this is square root of L times L plus 1, square root of that times Planck's constant divided by 2 pi. Let's calculate it. That's going to be the square root of 1 times 1 plus 1 times 6, well, we'll say h over 2 pi. L is a square root of 1 times 2 is 2. Square root of 2. H, Planck's constant, is 6.626 times 10 to the negative 34 joules seconds. Divide by 2 pi. The angular momentum, the orbital angular momentum for this electron is 1.491 times 10 to the negative 34 kilograms meters per second. Meters squared per second, sorry. That is the orbital angular momentum of the electron. Again, remember, orbital angular momenta are separately quantized from their direction. This is a quantum, there's a quantized value. Not all values are possible. Only values that are given by allowed orbital angular momentum quantum numbers. Again, it's not like the classical world where any orbital angular momentum goes. Only specific quantized values are allowed. The submicroscopic universe is much, much different than the classical universe in which we normally live in. Okay. All right, let's parking lot this answer. So for part A, kind of for future reference here, angular momentum 1.491 times 10 to the negative 34 kilograms meters squared per second. All right, let's do the spin. Do part B now. Part B says, again, we want to do what? We want to calculate the magnitude of the electron's spin. All right, well, remember, electron is a fundamental particle. Every fundamental particle has an intrinsic spin. For the electron, that value is simply 1/2. Again, if you're talking about a neutron, it's 1/2. A proton, it's 1/2. If you're talking about a photon, it's 1. If you're talking about let's say a pion, it's 0. Every fundamental particle in the universe has an assigned spin. All right, electron, it's 1/2. So what is the spin angular momentum? Well, it's given as S, cap S. It's the square root of little s times little s plus 1 times h over 2 pi. Again, so that's going to work out to be the square root of 1/2 times the quantity 1/2 plus 1. Okay, all under the square root sign times h over 2 pi. The spin angular momentum. Again, so if you put all that together, you end up getting that that's a square root of 3/4. Times 6.626 times 10 to the negative 34 joules seconds. Divide by 2 pi. The spin orbital angular the spin angular momentum of the electron is 9.133 times 10 to the negative 35 kilograms meters squared per second. That is the answer to part B. The electron spin, angular momentum. Put that in the parking lot. B, again, spin angular momentum, capital S, 9.133 times 10 to the negative 35 kilograms meters squared per second. All right, we're going to use these values in a moment. We want to determine the ratio of the two now. So the last part is pretty easy. So we calculate these two angular momenta that describe the electron, this particular electron. What's the ratio? Well, the ratio, I'm not going to actually do these two values directly. I'm going to kind of do it in a more clever way. But let's just calculate in general L over S. Again, the orbital angular momentum, capital L, divided by the spin angular momentum, capital S. Well, let's see. What are the general formulas for these again? Okay, so for L, it's the square root of L times L plus 1 times H over 2 pi. S is, again, the square root of S times S plus 1 H over 2 pi. I don't have to worry about Planck's constants, but I can actually cancel out the H over 2 pi's. What I get is I get a ratio of these square roots of quantum numbers. It's a much prettier way of doing this. So let's see, what did I have again? That's right, L equals 1 was my electron. Square root of 1 times 1 plus 1 in the numerator. And denominator is the square root of 1/2 times 1/2 plus 1. And I don't have any units over on these any longer because they are nothing more than a ratio, they're a unitless ratio. All right, so this becomes cap L over cap S. Becomes, let's see, I have 1 times 2 is 2, is square root of 2. Numerator divided on the denominator, I have, again, as I said, I have the square root of 3/4. This becomes really an arithmetic problem at this point. All right, so I still have the square root of 2 on top. On the bottom, I have, remember, a square root of a ratio is a ratio of the square roots. So on the bottom, I can write this as a square root of 3 over the square root of 4. Square root of 4 is 2, right? So I can write this as a square root of 2 over the square root of 3 over 2. And I can then multiply the top and bottom by the inverse of this ratio. And I can get that cap L over cap S will be 2 square root 2 over the square root of 3. If I work this out, this becomes 1.63. So the ratio of the orbital angular momentum for the L equals 1 electron divided by, or the ratio of that and its spin angular momentum is 1.63. All right, we have one more topic in this chapter, and that's really putting it all together. So now, interestingly enough, I want to point out one other thing regarding spin. So remember when I talked about solving the Schrodinger equation. Okay, so again, when we solve the Schrodinger equation, we get wave functions, we get multivariate wave functions, multivariate complex valued wave functions for the solution. again, I told you what they look like. Psi of r, theta, phi, and t, right? Now, I told you that I can also write this as a product of one-dimensional solutions. R of r, a cap theta of theta, and a cap multiplied by a cap phi of phi, and a cap t of t, if you will. Now, I told you that R of r was described by, we had a quantum number to corresponding, it was n. And the one for cap theta, quantum number that corresponded to it was the orbital angular momentum quantum number L. And for cap phi of phi, the quantum number that was the associated quantum number is m sub L. Where does the spin come into play? Well, Schrodinger's non-relativistic quantum mechanics does not predict spin. Quantum spin is predicted by Dirac's relativistic quantum mechanics. Spin is a relativistic phenomenon. Okay, so Schrodinger's non-relativistic quantum mechanics does not predict spin. There's no place for it in his theory. We need the Dirac relativistic quantum mechanics to describe spin. Spin is a purely relativistic phenomenon. All right, you cannot describe it. It has no place in a non-relativistic theory. So just like the photon, as we said earlier, the photon is a purely relativistic particle. That a photon makes absolutely no sense in a classical theory. Well, in a non-relativistic theory, you do not have any, spin does not appear to have any association. It is additional. You require relativistic quantum mechanics to describe spin. Okay, so it is purely a relativistic formula or a relativistic function. Now we're going to put it all together. I just want to make that statement real quick. Very important statement. Now we're going to put it all together and we're going to apply quantum mechanics to atoms in general. Okay. So we haven't really been specifically talking about atoms or the periodic table, but we now want to apply quantum mechanics to multi-electron atoms. I.e., atoms which contain or which possess 2 or more electrons. Okay, so in the neutral state, every atom in the periodic table is a multi-electron atom except hydrogen. So every atom in the periodic table, and you come into this class, I mean, I've shown you periodic table, you come into this class knowing that, of course, your chemistry experience, but every atom in the periodic table is a multi-electron atom, except for hydrogen. All right, so again, the physical and chemical properties of elements are directly related to the number of electrons a neutral atom has. We're going to talk a little bit about, we're going to talk a lot about chemistry here. So the physical and chemical properties that an atom has depends are directly related to the number of electrons. Oh, sorry. Yeah, the physical and chemical properties that an atom has are directly related to the number of electrons it has. Okay, so again, we're going to look at the entire gamut of all atoms. Now, again, you come into this class with knowledge of the periodic table. The periodic table, is a systematic array of atoms arranged by their atomic number. Z. And that's the number of protons it has. Number of protons in its nucleus. Now I will show you a periodic table, one of my favorites in a moment that I have on my computer. So again, we now want to apply quantum mechanics to multi-electron atoms, i.e. atoms which possess 2 or more electrons. So far, we've only been talking about atoms that have 1 electron, with the exception, of course, of let's say the X-rays, but I kind of pretended that it was like a multi-electron. I was a 1 electron atom. Okay. Every atom in this neutral state in the periodic table is a multi-electron atom, except for hydrogen. And the physical and chemical properties an atom has are directly related to the number of electrons it has. All right. And we can see this in the periodic table. So here's where all of our previous work is going to come into play. And it's a very famous principle that certainly you've heard about many times in your chemistry class. And allows us to build any atom that we want from quantum mechanics. All right, so in 1925, the Austrian physicist Wolfgang Pauli proposed the following rule. He says, no two electrons can have the same set of quantum numbers. No two electrons in an atom can have the same set of quantum numbers. Now, Pauli was an interesting character. A lot of times, the great quantum physicists would get together and they all had their various qualities. Some of them were more argumentative than others. Pauli was kind of a naysayer. So Pauli would get up there and he would propose something, and Pauli would argue against it all the time. Pauli was famous for one time saying, he wrote on a board, he says, "Here is the proof that I'm the greatest artist in the world. All that's left for me to do is fill in some details." Because somebody had proven, well, he's got to put in some details, and then Pauli goes up and basically draws a rectangle and says that's proof that he's the greatest artist in the world. All that was required are some details. I mean, again, Pauli just, Pauli's one of those guys that just was constantly, argumentative. He and Dirac would argue all the time. So anyway, and of course Niels Bohr, the same thing. Heisenberg as well. I mean, they got any great arguments. They said that Heisenberg and Bohr would work together, and oftentimes it became so fierce that Heisenberg would run away crying, literally. And so because Bohr was so impossible, So again, there's these great. So Pauli is one of these very argumentative kind of people. There's a lot of personality in these quantum physicists, are not just names. So anyway, this was a very powerful proposal. And so what this really means is that no two electrons can be in the same state. It's another way of writing it. So no two electrons can be in the same state. Okay, and we mean this by a quantum state. The statement is known as a Pauli Exclusion Principle. So this statement is known as the Pauli Exclusion Principle. And you've heard about this in your chemistry class. Very important for chemistry. In fact, atoms are built on this very principle. All atoms are built on the Pauli Exclusion Principle. We wouldn't have a universe without it. Okay, so essentially, the Pauli Exclusion Principle applies to any identical particles with half integral spin. Remember, one of the things about quantum mechanics is every particle is an identical twin. And there's a concept what's called indistinguishability. Indistinguishability is a concept that drives the nature of the statistics. Can I tell one electron from another? Can I label electron as electron 1, electron 2? The idea is you absolutely cannot. All electrons are indistinguishable. That means that very concept drives the statistics of the electrons, all right? And so now there are two types of particles in the universe. There's particles that have half integral spin and particles that have integral spin. All right, so there are two types of particles in the universe. One, particles of half integral spin. i.e., S can be 1/2, 3/2, etc. S equals 1/2. Well, that's a fundamental intrinsic spin for what? Electrons, protons, and neutrons. All of those are half integral particles. Any particle that has half integral spin is called a fermion. Any particle when I talk about particles, I'm really any particle with half integral spin obeys Fermi-Dirac quantum statistics. Including the Pauli Exclusion Principle. All right, and so you have the, and again, I have limited whiteboard space, but again, two types of particles. The first type are ones that have half integral spin. S, the spin quantum number, 1/2, 3/2, so on and so forth. Electrons, protons, and neutrons are all spin 1/2 particles. Any particle that has half integral spin obeys what is called Fermi-Dirac quantum statistics. That is the quantum statistics that when we talk about quantum mechanics, it's fundamentally based on statistics. That is the form of the statistics that half integral particles take on. And half integral particles, part of that statistics is the Pauli Exclusion Principle. The other kind of particle, number 2, are particles with integral spin. So integral spin would be integers. So what's an example of that? 0, 1, 2, ... So what's an example of particles of integral spin? I gave you some examples. Particles of integral spin. Let's see, a photon. A photon is a spin 0 particle. I'm sorry, spin 1. All photons have spin 1. All pions have spin 0. Okay, particles. Oh, by the way, particles, I forgot to tell you this. Particles that have half integral spin and again, they obey the Fermi-Dirac statistics, are called fermions. Fermions, electrons, protons, and neutrons are fermions. And this is after the great Italian physicist Enrico Fermi. Particles with integral spin are called bosons. And they obey Bose-Einstein statistics. Quantum statistics. Bosons do not obey the Pauli Exclusion Principle. You can throw all the bosons in one state. You can collapse them in one state. So the Pauli Exclusion Principle, when you go into more advanced physics, It's based upon the statistics. Now, again, you literally will go straight from statistics, what they're called like the number of ways of doing something called combinatorics. And you base the combinatorics, combine it with the concept of indistinguishability. You will literally derive either the Fermi-Dirac statistics for fermions or the Bose-Einstein statistics for bosons. Now, we're very fortunate that electrons and protons and neutrons are fermions. Otherwise, we wouldn't have matter. We wouldn't have a universe. We wouldn't be having this conversation. All right. So how does this apply here? What do you mean by a state? Okay, a state is like an address for an electron. It's like, what's your home address? Everybody has a home address or social security number. Well, an electron in an atom is determined by its state. Okay, so the state of an electron in an atom is determined by a unique set of quantum numbers. Now let me say this for a moment here. So you said quantum numbers. So what are the quantum numbers? Well, I'm going to write it down. It's N, L, M sub L, M sub S. Now notice I didn't put down S. No, so in this situation, S is redundant. Since it is always 1/2 for electrons. It doesn't make every electron in the universe is going to have S equals 1/2. So there's nothing special about that. All right, so we don't bother putting it in the address. All right, so any electron is going to have unique N, L, M sub L, M sub S combination. No two electrons will have the same N, L, M sub S, M sub L, M sub S. That is what Pauli Exclusion Principle tells you. All right, so the Pauli Exclusion Principle states that no two electrons have the same set of quantum numbers, the same set. So no two electrons, it isn't possible. No two electrons in an atom will share the same set of N, L, M sub L, M sub S, i.e. they do not have the same quantum state. A quantum state is given by this address. Okay, so basically we have this combination of electron filling. How do electrons fill an atom? All right, so first of all, as we saw, we have the principal quantum number N. N determines the energy state in the absence of magnetic field. So N determines the energy state in the absence of a magnetic field. And it's a principal quantum number. Essentially, it determines the energy level. So N determines the energy level. We saw this with, the hydrogen atom. Hydrogen atom, the energy levels, the orbits, dependent on N. So once you consider an N, then you have to start using the selection rules to fill up, look at the possible determination of L's and M sub L's and M sub S, right? And so essentially, a value of N, well, let's give an example. All right, so again, we've seen this before. So let's say I have an orbit. Let's say I start off with the value n equals 1, the lowest value I can get, ground state, n equals 1. All right, so let's consider n equals 1. Lowest principal quantum number possible, n equals 1. All right, well, what are the possible values of L? So remember L can equal 0, 1, 2, dot, dot, dot to n minus 1. Well, if n equals 1, that means the only value that L can have is 0. So L can only be 0. What about m sub L? Well, m sub L can have the values of negative L plus 1, dot, 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 negative 1, 0, positive 1, dot, 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 L minus 1 to L. So it can go from negative L to L. Well, L is 0. What does that say about m sub L? M sub L in this particular special situation is stuck at 0. It can only be 0. And what are the values of m sub s? Well, m sub s is always plus or minus a half. Doesn't matter. Plus 1/2 or minus 1/2. So if I'm looking at n equals 1 electrons, there are only 2 addresses possible. Right? There are only 2 addresses. Or there are only 2 quantum states possible. For electrons with n equals 1. And that is n, L, m sub L, m sub s equal to what? N equals 1, that forces L at 0, that forces m sub L at 0, and I can have 2 possible values of m sub s, plus 1/2 or minus 1/2. So one state would be 1, 0, 0 plus 1/2, and 1, 0, 0 minus 1/2. So one electron is spin up, the other electron is then spin down. 1, 0, 0 plus 1/2, 1, 0, 0 minus 1/2. All right, and so we have this concept now of a shell or a subshell. All right, so n equals 1, a value of n determines what is called a shell. Okay, so the value of n determines a shell. Now you've heard these concepts in your chemistry class as well. All right, so the value of n determines a shell, an electron shell in an atom. Okay, the value of L determines a subshell. In a shell. We have this termination of shells and subshells. A shell is given by a particular value of n. A shell is given by a certain value of n. A subshell of a shell is given by a certain value of L. All right, and so we have this concept of building an atom now. Now we're going to build up an atom. All right, so the idea is, with the, we start off again, an atom builds with principal with ascending principal quantum numbers. I.e. n equals 0 first. I'm sorry. N equals 1 first. We take our n equals 1 first. Then n equals 2. Then n equals 3. Dot, dot, dot. Right? You get the picture. And then for each value of n, the subshells, or for each value of n, i.e. the shell, each subshell fills in ascending order starting with L equals 0, then L equals 1, then L equals 2, and so forth. Right? This filling mechanism is based upon minimizing the energy. Okay, and so essentially it is it's the way the distributions, the electron cloud distributions, probability distributions, as they get nearer the nucleus, that's what determines the filling. All right. And so again, this ordering is based upon how close the probability distributions are to the nucleus. All right. And so the shell filling, the shell and subshell filling order depend on how close the corresponding probability distribution is to the nucleus. So states with the closest probabilities fill first, right? So states whose probability distributions are closest to the nucleus fill first. This is also a energy minimization process as well. So you can think of shell filling as an energy minimization process. Where lower energy states are filled before higher energy states. I mean, that's why this filling occurs the way it does. Okay. Okay, so with that said, and again, there's designations for these shells and subshells. I mean, I've talked about this already, but you know, again, the shell is always given by, there's always an NL type of a nomenclature, right? And so, again, the shell is given by a value of the principal quantum number N. The subshell is given by L, right? So an electron in a shell N and subshell L is described by nomenclature NL, as I said earlier, where N is the numerical integral value of the principal quantum number and L is given a letter designation. According to all right, so again, I wrote this table, but you imagine, you know, the value of L, again, this is the orbital quantum number, orbital angular momentum quantum number, and then the letter symbol. All right, so the value of L and the corresponding letter symbol. Again, L can take on, I'll just give 1, 0, 1, 2, 3, 4, 5, 6 would be the numerical value of the orbital angular momentum quantum number. The corresponding letter, again, this is from the old spectroscopic notation. Little s is, an s electron is one that has a value L equals 0. A p electron is one with a value of L equals 1. A d electron is one that has L equals 2. An F electron has L equals 3. Then after that, it goes to the alphabet. G for 4, H for 5, I for 6, and so on and so forth. SPDF notation you may have heard in your chemistry class. So if an electron has an L equals 0, it's called an S electron. If it has an L equals 1, it's called a P electron. L equals 2 is called a D electron. L equals 3, an F electron. L equals 4, a G electron. L equals 5, an H electron. L equals 6, an I electron. All right, and so for instance, if I'm looking for an N equals 1 state where L equals 0, it would be called a 1s electron. So for instance, if I have an N equals 1 state, and hence L equals 0. This would be a what? NL, right? So NL, so it's a 1 for N, and 0. What's 0? Oh, that's S. It would be considered a 1s electron. So electron that is sitting, what has N equals 1 and L equals 0 would be considered a 1s electron. If there are two such electrons, it'd be 1s2, right? Two electrons with that state, 1s2. If L equals 1, let's say N equals 2. Let's say another example, N equals 2, L equals 1. What example would that be? Let's see, N equals 2, that's a 2. L equals 1, that's a P. That would be a 2p electron. And so we designate a label on electrons based upon what their shell value and their subshell value are. Now, how many electrons? Let's do an example. How many electrons can be in a shell? So let's take a look at it. Let's go fill up a shell and see how we do that. All right, I'm gonna do example 30.4 from OpenStax. All right, OpenStax example 30.4. All right, list all possible sets of quantum numbers. For the N equals 2 shell. And determine the number of electrons that can be in the shell in each of its subshells. Okay. Okay, so here we go. So list all possible sets of quantum numbers for the N equals 2 shell and determine the number of electrons that can be in each of its shells and subshells. Okay, so I need real estate here. All right, so we're told that N equals 2. So what are the possible values, number one? Again, we're going to go back to the selection rules that we talked about earlier. N equals 2, L can equal 1. Well, again, L can equal, remember, L can be 0, 1, 2, ... to N minus 1. That means that L can equal 0, 1, or 2 in this situation. I'm sorry, 0 or 1. It can only go to 1 less than the principal quantum number. So L is 0 or 1. What about M sub L? Well, M sub L, remember, can be negative L plus 1, ... negative 1, 0, 1, positive 1, ... L minus 1 to L. So if L can be at most, so when L is 0, M sub L is 0. When L is 1, M sub L is negative 1, 0, or 1. All right, so M sub L be negative 1, 0, or 1. So again, there's a conditional here. If L equals 0, M sub L can only equal 0. If L equals 1, M sub L can equal -1, 0, or +1. And what about the spin? M sub S is always -1/2 or +1/2. Okay, this is from my selection rules. So let's build up the atom. So building it up, I can say, okay, well, let's just kind of write out N, L, M sub L, M sub S. Again, we're going to start filling up. So we know we are told that N equals 2. All right, so in each case, N is equal to 2. We're trying to figure out how many electrons, what are the designation of the electrons that can go in this shell? Well, we'll start filling up with, again, we always start filling up with lowest subshell first going to highest. So again, L can be 0 or 1. So we start off by saying, okay, let's let L equals 0. Lowest L first. Well, if L equals 0, that forces M sub L to be 0. Okay, by the selection rule. So if L equals 0, M sub L has got to be 0 by the selection rules. Well, there's two possible spins. Spin +1/2, spin -1/2. So I have one that's spin +1/2, and I can write this out as 2, 0, 0, -1/2. Again, those are two electrons that can go in the 2s shell or 2s subshell. Sorry. What about okay? So now that's it. That's it for L equals 0. Now L can be 1 as well. So now we look at the case again. We're still talking about an N equals 2 shell. Now we let L be 1. Well, if L is 1, that means the possible values of M sub L are -1, 0, or +1. So let's consider the case of +1. +1. +1 can have the value of, again, I always have two spins. +1/2, 2, 1, +1, -1/2. L can also be 0, 2, 0. I'm sorry. L is 1 still, sorry. M sub L can be 0, 2, 1, 0, +1/2, 2, 1, 0, -1/2. Or M sub L can be -1, 2, 1, -1, +1/2, or 2, 1, -1, -1/2. All right, so again, I'm loading up the N equals 2 shell. All right, so again, if N equals 2, L could be 0 or 1. If L is 0, M sub L is forced to be 0. There's two possible spins, a spin up or spin down. Okay, the L and M sub L can only be 0. If I let L equal 1, the M sub L could be 1, +1, 0, or -1. And in each case, each one of those can have a +1/2 or -1/2 spin. So there are a total of, these are the 2s electrons. Why? Because N equals 2, L equals 0. I have a total of 2, as you can see. And these are the 2p electrons. Again, N equals 2, and L equals 1. And I have what? 1, 2, 3, 4, 5, 6. I have 6 of these. I have two electrons that can fit in the 2s state, and 6 electrons that can fit into the 2p state. All right, so that essentially is telling me that I have a total of 8 electrons. So a total of 8 electrons in an N equals 2 shell. That's it. 8 electrons, 2 in the 2s and 6 in the 2p. All right. Now, the big question is, how many electrons can actually fit in a shell? Is there a general formula? So first of all, I can figure out how many can actually fit into a subshell. All right. In general, Again, I'm not gonna, again, that's the answer to this example, but in general, I'm gonna kind of keep this up here. In general, the number of electrons that can fit into a subshell with quantum number, or with angular momentum quantum number L, with angular momentum quantum number L is, okay, let's think about this for a moment. I have what? If I have L equals 0, then m sub L can only equal 0. If I have L equals 1, m sub L can equal -1, 0, or +1. If I have L equals 2, m sub L can equal -2, -1, 0, +1, +2. If you look at it carefully, the number that can fit, the number with the subshell designation in this particular order would be what? It'd be 2L plus 1. If L equals 0, 2 times 0 is 0, plus 1 is 1. Okay, only one m sub L value possible. If L equals 2, 2 times, I'm sorry, if L equals 0, if L equals 0, 2 times 0 plus 1 is 1. There's only one m sub L value. If L equals 1, 2 times 1 is 2 plus 1 is 3. 3 m sub L values. If L equals 2, 2 times 2 is 4 plus 1 is 5. 1, 2, 3, 4, 5 m sub L values. But do not forget, for every one of these combinations, there are 2 spins, spin up and spin down. So it's actually 2 times 2L plus 1. So for a given orbital angular momentum quantum number L, which denotes a subshell, the total number of electrons you can fit in there is 2 times the quantity, 2L plus 1. So with that said, and we see this, right? When L equals 0, 2 times 0 is 0, plus 1 is 1. 1 times 2 is 2. There it is, 2. 2 for the L equals 0 subshell. If L equals 1, let's see, 2 times 2 is 1. That's, so I'm sorry, 2 times 1 is 2, plus 1 is 3. 3 times 2 is 6. 6. So again, 6 in the L equals 1 subshell. 2 times the quantity, 2L plus 1. That is the number of electrons that can go into a subshell with orbital angular momentum quantum number L. 2 times the quantity, 2L plus 1. How many electrons will fit into a shell? This is the number going to a subshell. How about a shell? How many electrons? Remember this. 2 times 2L plus 1. Now we ask the question, how many electrons can fit into a shell? So how many electrons can fit into a shell N? How do you figure that out? Well, call that capital N. It is the summation of what? L equals 0 to N minus 1. That's the biggest value that L can be. Of what? Well, every single subshell is going to have 2 2 times the quantity, 2L plus 1 electrons in it. All I'm doing is I'm adding all the electrons for each subshell in a general mathematical way. Summing from L equals 0 all the way up to the biggest value that L can be, which is n minus 1. All right, for a given shell n. So that's going to equal what? That's going to equal, taking this apart, I have the summation L equals 0 to n minus 1. 2 times 2L is 4L. Plus the summation L equals 0 to n minus 1 of 2 times 1 is 2. So I can pull this 4 out in front. Now, we're going to use a special formula that was first devised by the boy, Carl Friedrich Gauss. Remember, Carl Friedrich Gauss was a child prodigy. He got in trouble one time. One of the things that the German schoolmasters would do is make you go and add up the first 100 numbers. Gauss came back and in a few seconds had it all figured out. And what Gauss figured out is the sum of the first n numbers, n integers, is n is equal to n times the quantity n minus 1 divided by 2. So if you add up, let's say I want to add up the first 3 numbers, 1 plus 2 plus 3, what would that be? 6. Does this work? Well, we want to first add up how many numbers? The first 3, right? So that would be 3 times 3 minus 1 divided by 2. Let's see. I'm sorry. It's it's n times n plus 1 over 2. Apologize for that. N times 3 plus 1 over 2, or 3 times 4 over 2, which is 6, right? So Gauss, as Gauss showed, again, this is due to Gauss. Again, the same Gauss as in Gauss's law for electricity and magnetism. Gauss was a mathematical prodigy. So Gauss is a little boy, he's probably about 7 years old, showed that if you add up the first n numbers, it corresponds to this formula. We're going to use Gauss's formula right here. And we want to add up, so we're going to have to fix it up a little bit. But if we use Gauss's formula, I can literally write, using Gauss's formula, I can literally take the summation, again, it's the first n minus, it's really the first n number starting counting from 0. I can use Gauss's formula and say that I have 4, and then I can use Gauss's formula and say, well, this is n minus 1 times n divided by 2. Again, using Gauss's formula. If I add up n 2s, I just get 2n for this one. This one's pretty easy. That second summation. Again, this is Gauss formula. All right, do a little bit of algebra. I have n equals, let's see here. 4 divided by 2 is 2, so 2n squared minus 2n plus 2n. And so I find out that it's equal to 2n squared. That is how many electrons will fit into a shell n. Does that work here? Let's see. What did I say this was? I said this was n equals 2, right? So n in this case is 2 times 2 squared. 2 times 4 is 8. 6 plus 2 is 8. Yes. So for a shell n, the total number of electrons that fit into a shell n is 2n squared. The total number of electrons that go into a subshell given by L is 2 times the quantity 2L plus 1. And these are very important formulas that really we use to fill the atoms in a periodic table. All right, and so again, let's talk about this. Let's see how we can fill atoms or fill up electrons in atoms. All right, and so we start off understanding that. Let's start off with, for instance, and we're going to kind of use this SPDF notation. And so if we look at hydrogen, Okay, the first element, hydrogen. It has 1 electron. If I look at it, let's just kind of draw it out here. So element, number of electrons, and what is its ground state configuration? Hydrogen is the simplest one. I only have 1 electron. So again, let's take a look here, right? I have N, L, M sub L, M sub S, right? If N equals 1, again, I'm looking at the ground state, the lowest possible value, right? N equals how many? I'm gonna go from the lowest state. So if N equals 1, that means that, again, let's kind of look at this here as I fill it up. N equals 1. So I'm going to start from the lowest value, lowest possible value. That means that L must be 0. That means that M sub L can only be 0, and M sub S can only be plus 1/2 or minus 1/2 when I start filling. Again, I got to start from the lowest N. So hydrogen is going to start off with the lowest N. So again, it's hydrogen, 1 electron. And so I'm going to get it the lowest one. So let's just say, for instance, and I would say, well, it's going to be what? It's going to be an electron. That's how many can I fit in here? Well, I can fit 2 of them in the 1s configuration. Again, this would be, there are 2 electrons in 1s configuration. They are, again, N, L, M sub L, M sub S. Either 1, 0, 0 plus 1/2, or 1, 0, 0 minus 1/2. All right, and so putting them in this configuration, I can put 1s electron in here, 1s1. Now I can, for helium, helium has a 2nd electron. So what do? Well, I can go, again, I'm going to go from the lowest N and the lowest L and progress. Well, there's 1 more electron I can fit into that shell. And so it has 2 electrons, so I can actually fit 2 electrons in the 1s shell. That closes up that shell. I can't put any more electrons in the 1s shell. That is it for helium. That is it. Hydrogen and helium are the only 2 atoms that where both electrons fit in the lowest, in the 1s shell. And I go to the 3rd element, lithium. Lithium is element number 3, 3 electrons. I can put I can put the first 2 electrons in the 1s shell, but then I have to go now to 2. I now have to go to N equals 2. I have 3 electrons. Okay, so for N equals 2, L can go 0 and then 1. M sub L would be 0 for L equals 0, or -1, 0, +1 for L equals 1. M sub S, as always, is plus 1/2 or minus 1/2. All right, so for lithium, my 3rd electron has got to be in a N equals 2 state. All right, now the question is, well, what do? I have N equals 2. I fill out, again, I fill up the L value starting from the lowest value. So again, I have another L equals 0 state. So the lowest state, it could either be N, L, M sub S. Well, again, I would go as, again, I'm N equals 2, but I'm going to go starting from the lowest value of L, which is 0. Again, if L is 0, I'm stuck with M sub L being 0. I have 2 ways to make that happen. 2, 0, 0 plus 1/2, or 2, 0, 0 negative 1/2. All right, so I can start filling up. I can fill out, and I don't go to P yet. I can put 2 electrons in the S shell. So I'd say 2s1. That's lithium, and I'm done. What's the next one? Beryllium. Beryllium is 4 electrons. All right. Well, again, I could stick 1 more electron in the S shell. I always want to go from low energy to high energy. So it would be 1s2, 2s2. Now I have filled up the S shell, the 2s shell. I can't put any more electrons there. What do I do now? Well, now I go to the P shell. I go to L equals 1. I start filling up those electrons. How many ways can I do that? Well, again, I have 6 possible electrons I can stick in there. I don't know which one. But anyway, it's N, L, M sub L, M sub S. Okay, so I'm done with the L equals 0. So I'm stuck with 1. Well, I can go, what, 2, 1, negative 1, negative a half, 2, 1, negative 1, positive a half. Again, 2 spins. 2, 1, 0, negative a half. 2, 1, 0, positive 1 half. 2, 1, plus 1, positive 1 half. Or if I can fit on here, 2, 1, negative 1, negative a half. So let me just do one more here. 2, 1, negative 1, negative a half. So these are 2 p electrons. N equals 2, L equals 1. So how many of those do I have? 1, 2, 3, 4, 5, 6. Now there's no way of knowing in quantum mechanics which one of these states that I'm actually going to fill up. I'm going to fill out one of them. So I start filling out the 2 p's. I have 2p1. And as you progress along the periodic table, what's the next one? Boron. I have 6 of these. I'm going to fill out the 2p shell. All right, and so I have 6 of these 2p electrons to fill out. So I go boron, element 5, 1s2, 2s2, 2p2. Then I go to carbon, which is 6, 1s2, 2s2, 2p3. I'm filling out the p shell. Okay, what's next? Nitrogen. Nitrogen is number 7. Again, that's 1s2, 2s2, 2p4. Again, I go to oxygen. 8, 1s2, 2s2, 2p5. And finally, I get a full shell, which is neon. Oh, I'm sorry. That's not right. Beryllium. Oh, I messed up. Sorry about that. All right, so I apologize. The lithium and beryllium are the ones where I'm filling out just the 2p, the 2s. Now the 2s is full. I go to boron. I start filling out the 2p. I apologize. 2p1, 2p2, 2p3, 2p4, and then, I'm sorry, fluorine, 9th one, 1s2, 2s2, 2p5, and finally to fill out to the noble gases, neon is number 10, 1s2, 2s2, 2p6. Now, there are no more electrons that I could put in an N equals 2 shell. This is why this is a noble gas. It is as happy as can be. It has a complete N equals 2 shell. I cannot put any more N equals 2 electrons. Okay, this is a noble gas neon. If I were to continue to the next one, let's say sodium, I'd have to put a 3s1 there. So if I go to sodium, and that has 11 electrons, it would be 1s2, 2s2, 2p6, and I start developing the 3s1. If I move on to magnesium, again, what do? I start filling out the lowest L values first. So again, in this particular case, L can be I mean, I am now at n equals 3. So L could be 0, 1, or 2. All right. And so in this particular case, I start off with the L equals 0 first. 1s2. 2s2. 2p6. 3s2. So again, I filled out the S subshell. S subshells can only take 2 electrons. P subshells can then take 6. So again, aluminum, silicon, phosphorus. So aluminum, silicon, phosphorus, sulfur, chlorine, argon. It's the same process. Now I have L equals 1. That's a p electron. Again, as I said earlier, there's 6 electrons I can fit in that subshell. I'm still filling out the 3s, the n equals 3 shell. So atomic number 13, 14, 15, 16, 17 to 18. All right. So again, they all end up being 1s2, 2s2, 2p6, 3s2, 3p1, same deal, 3p2, 3p3, 3p4, 3p5, and 3p6. So again, this final one would be what? 1s2, 2s2, 2p6, 3s2, 3p6. Again, if I were to go on, my first exception to the rule would be potassium. Potassium, and then follow that with calcium. What I end up doing now, you would think, okay, well, you still have now you said you have L equals 0, L equals 1, L equals 2. Those are Ds. You should start having some 3D electrons. But interestingly enough, the next filling that happens for potassium is actually 4s electrons, because those electrons are closer to the nucleus, the probability distributions. If I go to 19 and 20, 19 would be 1s2, 2s2, 2p6, 3s2, 3p6, then 4s1. We start having an exception to the rule. If my rule followed, I should start filling out 3Ds. And then, of course, I fill out to complete the S shell, but calcium would be 1s2, 2s2, 2p6, 3s2, 3p6, 4s2. Again, the first exception to the rule would be to fill out calcium. All right, and so again, it's all based upon the it's based upon the how close the probability distribution functions are to the atom. So again, I'm just going to kind of walk briefly through the periodic table, because essentially where an atom resides in the periodic table is going to be let me share my screen here. The chemical properties that you expect will be determined by where the how many electrons are in a valence shell. Okay, so I'm going to kind of talk through a lot of this you'd see in your chemistry class. So what you notice in a periodic table is that what we call periods are these columns that you see. And so what's nice is the arrangement of them are in accordance with basically how many electrons are in the outer shell. So if you look at hydrogen, it has 1 s electron in its outer shell. So does lithium. Remember, so helium is 1s1, 1s2. Lithium, you start building up what? 2s electrons. For sodium, you start building up 3s electrons. For potassium, we started building up 4s electrons. So for the entire what we call the alkaline earths, which is a very far left period, all of them have one thing in common. They all have one s electron in their outer shell. That's where the chemistry is done. It's done at the valence shells. If you look again at the very far right of the periodic table, you see helium, neon, argon, krypton. Those are the noble gases. And what they have in common is they have a full shell. Helium has a full n=1 shell. When you get to neon, it has a full n=2 shell. It means it has all of its 2s and 2p electrons, all that it needs. No other no other electron can be put in n=2 after you hit neon. So neon is happy as can be. It is a full shell. If you go to the next one, the third row down, the argon is a situation where it has a full argon has a full really a full 3s. It has 3s2 and 3p6. You start building you start building with the 4s electrons after argon. So again, argon is another noble gas. Now you can put more 3ds in there. That's the transition series. But again, all the chemical properties are determined based upon these, where they are in the periodic table. So if you look at it, the alkaline earths, the very far left column, the very far left period, only has one loosely bound electron to it. Has a full shell, which is one extra electron. It doesn't care at all about the electron. It can lose the electron. Those are metals. Those are the metals. All right, and so those are the ones you can lose an electron easily. Now, if you look at the halogens, which would be fluorine, chlorine, bromine, iodine, they have almost a full p subshell. They're just missing one. So they very badly want to complete their shell. So again, the alkaline earths, the lithium, sodium, potassium, they oftentimes form positive ions because they're perfectly happy to give up their extra electron. Whereas the fluorine, chlorine, bromine, the halogens, they oftentimes want an electron badly. And so oftentimes will carry an extra electron. So they oftentimes form a negative ion. So the chemistries that you see, the alkaline earths, the far left period, are highly, highly reactive. The halogens, the fluorine, chlorine, bromine, they're highly reactive. Why? Because they're seeking they either can give up an electron very easily or they want an electron very badly. And then, of course, the noble gases, they don't react at all. They're very inert. They don't want to react at all. So again, that's because they're perfectly happy. They don't have a desire to either give up an electron or get an electron. You can also take a look at, let's say, the period that contains carbon, silicon, germanium. They have very similar chemistries. The beauty about carbon is it can form bonds with so many different hydrocarbons. Carbon is the basis of life. And it's been theorized. And again, all of the life that we have ever seen on the Earth is carbon-based life forms. It is theorized that it is possible that there are life forms in the universe that are silicon-based. All right, and again, because silicon should have the same kind of chemistry as carbon. So the kind of chemistries, so again, you fill up the table based upon the Pauli Exclusion Principle. That's the filling. And again, based upon what electron you're filling, or are you filling a brand new 1s shell or whatever, that is where the placement of the element is in the periodic table. All right, I just kind of talked through that. I'm gonna work out 3 problems and the 3 more problems. I'll call this section done. I'll call this chapter done. So let's just work out really quickly 3 problems. I'm going to stop sharing. Okay. So let me look at OpenStax 30.44. All right, that says A. How many electrons can be in the n equals 4 shell? B, what are the subshells and how many electrons can be in each? All right. So again, 30.44, how many electrons can be in the n equals 4 shell? And B, what are its subshells and how many electrons can be in each? So again, we'll use the formula. So we're talking about n equals 4. So we'll use that nice formula that I derived a moment ago. Talks about how many electrons can fit into a shell. So part A, we know that n equals 4. The number of electrons that go into a shell is given by 2n squared. N equals 2n squared. Number of electrons that can go into a shell with n equals 4, or with, I'm sorry, with principal quantum number n. All right. Okay, so that tells me that n will be 2 times 4 squared, or 2 times 16 is 32. So for part A, I expect to be able to put 32 electrons in n equals 4. How would I designate those in terms of subshell? All right. And so again, we want to know what are the subshells and how many electrons fit in each one. So the n equals 4 shell can have 32 electrons. How do they get distributed? Okay. And so again, for part B, if n equals 4, then the orbital angular momentum quantum number can take on the values 0, 1, 2, or 3. So 2 times 2l plus 1 electrons fit into a subshell with L equal with subshell L. All right. So what kind of shells can I have? Well, again, I can have a 4, n equals 4. I can have a 4. Let's see, up to n equals 3. So S, P, D, F. I can have a 4 S, P, D, or F. Okay, that's how many I could put in here. Again, L equals can equal 1, 2. I'm sorry, 0, 1, 2, or 3. 0, 1, 2, 3, which corresponds, of course, to S, P, D, F. That's the symbol. How many? So how many? And that's given by what? 2 times 2L plus 1. 2 times 2 times 0 plus 1 is 2. 2 will fit into the S subshell. 2 times 2 times 1 plus 1. 2 plus 1 is 3 times 2 is 6. 6 can go into the P subshell. 2 times 2 times 2 plus 1. 2 times 2 is 4 plus 1 is 5. 5 times 2 is 10. Can go into the D subshell. And finally, in the F subshell, I have 2 times 2 times 3 plus 1. 2 times 7 is 14. You add all these up, you should get 32. 24, 30, 32. So again, the 32 shells and the 32 shells, I'm sorry, the 32 electrons in n equals 4 shell are distributed into the subshells S, P, D, and F, or 4S, 4P, 4D, and 4F in this manner. All right. 2 more problems. OpenStax 30.46. If one subshell has an atom, one subshell of an atom has 9 electrons in it. What is the minimum value of L? And B, what is the spectroscopic notation for the atom? B, what is the spectroscopic notation of the atom? If the subshell is part of the n equals 3 shell. Okay, so again, if one subshell of an atom has 9 electrons in it, what is the minimum value of L? And what is the spectroscopic notation of the atom if the subshell is part of the n equals 3 shell? All right, so how many electrons will go into a subshell? Well, we know that for part A, there are 2 times 2L plus 1 electrons that can go into a subshell. Well, let's just, and that's a subshell of value 9, or value L. So let's say, well, we know there are 9 electrons. As we're given, we're told that there are 9 electrons in the subshell. Let's try to get an idea of what value of L that we're talking about. So let's solve for this. So we'll divide both sides by 2. So 2L plus 1 is 9 halves. And then let's subtract 1. So 2L becomes 7 halves. Or this implies that L is like 7/4. All right. And so, well, L obviously cannot be 7/4. It's got to be an integer, right? So if you take a look at 7/4, well, this is telling you that you got to go to the next integer higher. So the next higher integer is L. Again, we want the minimum L is 2. So this means that the total possible number of electrons in the subshell. So again, it's missing 1, right? So again, so L min is 2. All right. And so how many possible? We see where there's 9 here. How many possible can actually go into that subshell? If L equals 2, so this subshell can hold 2 times 2 times 2 plus 1, or 2 times 5 is 10. So all available states in this L equals 2 subshell are occupied except one. Now, in spectroscopic notation, what would this be? Well, again, we're told we're in the n equals 3 shell. So it's 3 times some letter designation. Well, no, it's 2, right? So 0, 1, 2. SPD. So it'd be 3D. This is a 3D subshell. Again, S, it goes, L equals 0, 1, or 2 is SPD. So again, L equals 2 stands for D. This is a 3D subshell. And what would the spectroscopic notation be? It'd be 3D. How many electrons in there? 9. This would be a 3D9. This basically says that we're talking about what? N equals 3. We're talking about L equals 2, and we're talking that there are 9 electrons in that particular subshell. 3D9. Again, N equals 3, L equals 2. How many electrons in that subshell? 9. That's the notation. All right, last problem. Here we're going to look at, again, really hammering in the concept of selection rules and allowed states and unallowed states. So basically, Opus X 30.48, it simply says, which of the following spectroscopic notations are not allowed? Which of the following spectroscopic notations are not allowed? We're going to try to understand why. All right, so part A, it gives us 5s1. That's the notation. Well, let's see here. N equals 5. Yeah. L can be 0, 1, 2, 3, or 4. And so, and again, of course, M sub L can be -4, -3, -2, -1, 0, 1, 2, 3, or 4. And, M sub S can be plus or minus 1/2. Plus 1/2 or minus 1/2. So if n equals, this is telling me what? This is saying that n equals 5. This is saying that L equals 0. That's perfectly fine. L can be 0. And this is also telling me that there's 1 electron in there, and that's perfectly fine too. In fact, I can have a whole bunch of electrons in there. I mean, I can have what? I can have 2 times 2, let's see, 2 times 2 times 4 plus 1. I can actually have 18 electrons in there. I can have 18 here. So this is an allowed state. This is perfectly fine. I can have a 5s1 state. That's perfectly okay. N equals 5, L is 0, and I can have 1 electron in there. That's perfectly okay. That's allowed. What about so part B then becomes a 1d1. How about that one? 1d1. All right, what's this telling me? N equals 1, L equals, let's see, SPD. L is 2. That's nonsense, right? Because L can only have 0, 1, ... up to n minus 1. If n equals 1, the only value of L is 0. L can only be 0 for n equals 1. This is nonsense, not allowed. I cannot have this spectroscopic notation. It is impossible. It is not allowed. Okay, I cannot have L being a value greater than n. All right, part C is a 4s3. 4s3. What's that telling me? N equals 4, L equals 0, and I have 3 electrons in subshell. Well, N equals 4, L equals 0 is fine, right? Because L can have the value. Again, L could be 0, 1, 2, or 3. That's okay. But if L equals 0, if L equals 0, which is what we say, M sub L can only equal 0 only. So M sub S can either go plus 1/2 or negative 1/2. So that means that in this state, all I can possibly have are 2 electrons. So we can only have at most 2 electrons in a 4s subshell, not 3. That's nonsense. Again, this configuration is not allowed. Again, the selection rules tell you what states are allowed, what states are not allowed. Okay, how about 3p7? And so let's do part D. And that's the kind of logic in these problems. Part D, we're looking at a 3p7. What does that mean? Well, N equals 3, okay? L equals, let's see, SPD. Okay, that's 0, 1, 2. Oh, L equals 1. It's a p electron, L equals 1. All right, that's what P tells me, that L equals 1. How many, so in that case, M sub L can be negative 1, 0, or 1. M sub S can be plus 1/2 or minus 1/2. So I mean, if I have an L equals 1 shell, how many electrons can I fit in it? Well, again, 2 times 2L plus 1 electrons can fit into subshell L. What's that for L equals 1? That's 2 times 1 plus 1. That's 6, not 7. All right. So we can have at most 6 3p electrons, not 7. Okay. This one is not allowed. So again, then there's one more subsection here. Part E is 5G15. Okay, 5G15. What does that tell me? Well, it tells me N equals 5. Okay, let's see here. SPD FG. So 0, 1, 2, 3, 4. Okay, so that means that L must equal 4. So L equals 4 if it's a G. Again, SPD FG 0, 1, 2, 3, 4. Yes. So L equals 4. All right. So the question is, well, it's telling me, and this also tells me I have 15 electrons. Can I have 15 electrons? Okay, so again, by the SPDF notation, this is the value of L. This is the symbol, just roughly. Okay, that's why I figured out. SPDFG 0, 1, 2, 3, 4. L equals 4. How many electrons can I put in? It's telling me I have 15 electrons in this state. Can I have 15 electrons? Again, how many electrons? In subshell L. L equals 4. All right. How many? 2 times 2 times 4 plus 1, or 2 times 9, which is 18. I can have 18. I have 15. That's fine. So this is an allowed state. That state is perfectly okay. Again, I'm just using these selection rules that honestly that govern the Pauli Exclusion Principle and the electron filling of atoms. And that is it for this chapter.